In this fourth lecture on numerical integration, today we shall discuss Gaussian quadrature, numerical integration by Gaussian quadrature formula. Actually, Gaussian quadrature, it is the Gauss-Legendre quadrature formula that we shall be discussing. Earlier, we have discussed two methods for numerical evaluation of a definite integral. Both the methods based on the fact that the entire interval AB is divided into n number of equal intervals. It is found that when the integrand has oscillations or it has changes, rapid changes, then to get the convergent result, a huge number of integration point has to be used. As for example, consider a function which is of this sort. Then, so far this part is concerned, not much point is required to get convergent result, but high number of points is required for convergence of the result in this region. In Newton's in Simpson's 1/3 formula or trapezoidal formula, entire interval is given equal stress, which is not necessary at all over there. So the labor is wasted over there, while one could focus more attention in this region. And so if we choose if we could afford proper importance to the specific region, then integration or result can be obtained with less number of points and the result would be accurate one. Gauss, assuming this, he argued that the definite integration between two limits could be evaluated very simply by using few symmetric points in the interval and evaluating the function itself at those specific symmetric points, and they are multiplied by the appropriate weight factors. And by this way we could get a convergent result. As we estimate the function f as per Gauss, we are evaluating this integral I of x. This integral will have dimension of function f multiplied by x, and it is found to convert this equation into dimensionless form. So first we recast the equation integration in its dimensionless form. So our aim is to calculate x is equal to integration from a to v fx dx numerically. We introduce a variable u such that it is 2x by b minus a minus b minus a. We introduce so that if we put x is equal to a, at x is equal to a, we have u is equal to 2a minus b minus a by b minus a. So this is minus 1, because the numerator I have a minus b, and at x is equal to b we have u is equal to 2b minus b minus a by b minus a is equal to plus 1. So with this substitution, we could change the interval from minus 1 to plus 1, that is, we recast the integral in its dimensionless form, and dx is simply replaced by b minus a by 2 du. So we introduce the variable u is equal to 2x minus b plus a by b minus a, so that dx is equal to twice it is b minus a by 2 du, and the integration becomes and this result becomes b minus a by 2 minus 1 to plus 1 phi of u du. We call it b minus a by 2 I of u, where I of u is the integrand in u in terms of u. Since we have converted the interval from a to b to minus 1 to plus 1 and u is a continuous variable, we are heading towards the Legendre polynomial. As per Gauss, if we choose n symmetric points in the interval minus 1 to plus 1. By symmetric, we do not mean that the points are equispaced, rather they are the roots. By symmetric, we mean the roots of, they are the roots of special function. We shall come to this point later on. The point that I want to make clear, that by symmetric point we do not mean that the points are equispaced, but the points are distributed symmetrically about u is equal to 0, that much. Then choose n symmetric points in AB, then IU is equal to minus 1 to plus 1 phi of u du is, as per Gauss, is I is equal to 1 to n omega I phi of ui, where ui are such special points in AB and wi are the corresponding weights. It is the assumption of Gauss. Now we need to know, if we choose n such points, then we need to know n values of ui. So requirement is n values for each of wi and ui. That is to say, we need the value w1, w2 or weight factors up to wn and corresponding u1, u2, un. So we are to know 2n quantities. So this required 2n condition is required, 2n conditions are required. Guided by this, we express phi of u as summation over j from 0 to 2n minus 1 cj u to the power j. So we require 2n conditions. This is a polynomial of degree 2n. So sorry, polynomial having 2n terms. So it has degree 2n minus 2. Now writing explicitly, this becomes C0 plus C1u plus C2u square right up to C of 2n minus 2 u of 2n minus 2. This is the explicit form of it. Now if we integrate this function, this quantity, if we write u in this form, then we could get a form of iu. So if we write u in this form, iu is equal to integration from minus infinity to plus infinity fu du, which we write summation over j from 0 to cj here we have used this form of u, and the integration result is you see that when the power this j is odd, this term gets cancelled, and for even term they survive. So we get only for even values of j we have the sum, so we write it as this factor 2 c of 2j by 2j plus 1. J is equal to 0 to n minus 1. This is one way of evaluating the integral. So we write one form of it as this. iu, this is equation number 1. This is iu is equal to summation over j 0 to n minus 1 twice c of 2j plus 1. This is equation 2. We could write this expression of u over there to get another form. So, sorry, this should be the equation 2. This is equation 3 in that case. So if we write this as the representation, then we can write u in an alternative way. The alternative way of writing iu is summation over I is equal to 1 to n wi phi of ui, and for phi of ui you use equation 2. J ui of j. We compare this, we interchange the order of summation, so we write summation over j first, cj Then we have summation over I ranging from 1 to n wi uij. This is equation 4. The equation, if we compare equation 3 and equation 4, we get that coefficient, comparing equation 3 and 4, we get 3 and 4 gives summation over I is equal to 1 to n wi ui to the power j is equal to 2 by 2j plus 1 for j is equal to even and 0 for j is equal to odd, because there is no odd terms. So this is the basic equation which allows us to determine n points and the n corresponding weight factors. These 2n equation enables us to determine u's and w's unambiguously. This is the basic theory behind Gaussian quadrature. Let me write this expression explicitly. So we finally get a methodology for evaluating ui's and corresponding wi's. Let me write this equation explicitly. So the symmetric points, between the limits plus minus 1 are determined by this condition, ultimately by this condition. We take j is equal to 0. So we have w1 plus w2, w3 right up to wn. And since j is 0, this is 2. Then we take j is equal to 1. So it is w1 u1, w2 u2, w and un is equal to 0, because it is an odd, j is odd. w1 u1 square, w2 u2 square, wn un square. Now j is 2, so this is 2 by 3. w1 u1 cube, w2 u2 cube, wn un cube. This is 0 because j is odd. w1 u1 4, w2 u2 to the power 4, wn un to the power 4. It is 2 by 5. And w1 u1 5, w2 u2 5, wn un 5 is equal to 0. Now if we want a 1 point formula, that is we need one w1 and w1 and u1. So for this is 1 point form. For 1 point formula, these two equations are sufficient to give you u1 and w1. The equation for 2-point formula, we need to know 4 conditions. So this is the 2 requirements. These four equations are required for 2 points formula. Obviously they will get simplified. For 3-point formula, we need to solve these 3 equations. So for 1-point formula, we have, for 1-point formula, we have W1 is equal to 2 and W1 U1 is equal to 0. See, this gives U1 is equal to 0. So to say, we divide the interval -1 to +1 in 1 point, and this symmetric point must be 0. For 2-point formula, the equations are W1 plus W2 is equal to 0, the first equation. W1 U1 W2 U2, sorry, W1 U2 is 2, sorry, this is 0. Then W1 U1 square plus W2 U2 square is equal to 2 by 3, and W1 U1 cube plus W2 U2 cube is equal to 0. First thing, since the points are symmetric, we may assume that W1 to get 4 unknown quantities, we have to solve 4 equations. We may not solve the equation rigorously, but we can get the result. Since the points are symmetric, the weight factors have to be symmetric. So for 2 points formula, W1 is equal to W2. Obviously, this equation where this gives you U1 is equal to minus U2. That is to say, the interval between ±1 is divided at, this is U1 and this is minus U minus U1. So these points are symmetric about x is equal to 0. That is the meaning of symmetry. And obviously this is equal to 1. So if we put W1 is equal to 1 in this equation, this gives you twice U1 square is equal to 2 by 3, or U1 is equal to plus minus 1 by root 3. Now this equation at present is no more required because we have used symmetry argument. So we have obtained the U values. One remarkable similarity, we are considering 2-point formula. So Legendre polynomial of order 2 is given by half 3u square minus 1, and the zeros of P2 are plus minus 1 upon root 3. Accidentally, these are the symmetric points. Not accidentally, as I have told, it is basically Gauss-Legendre quadrature. If we go to 3-point formula, for 3-point formula we have we are to write these equations. Only thing is that there will be 3 terms, not more. So without going into writing the things in detail, I am just modifying this expression to get the result for 3-point formula. So this is equal to 2, this is W3U3 is equal to 0, this is W3 u2 square is equal to 2 upon 3 w3 u3 cube is equal to 0. w3 u3 to the power 4 is 2 upon 5. These are the conditions to which will these 4 equations are sufficient to solve to get the 3 u's and 3 corresponding w's. But one thing, the 3 points should be between, if we are looking for symmetric points between plus minus 1, then one u2 is this, and if we choose u1 over there, then the u3 must be equal to minus u1. This is a drastic simplification. And furthermore, w3 must be equal to w1. So this equation becomes very important. Since this is 0, this equation gives you this equation gives you simply u1 is equal to minus u2, rather this equation. This part does not contribute because u2 is 0, so we are w1 twice u1 square, because u1 and u3 are same, is equal to 2 by 3. So this is one important relation, and from this relation we get w1 and w3 equal, and this equation may be utilized to get the other result. This is twice w1 u1 to the power 4 is equal to 2 by 5. These two equations, when we solve these two equations, we get, when we solve these two equations, let me write, we first argue for 3-point formula. We argue that u2 is 0 and u1 and u3 must be symmetric, so u3 is equal to minus u1, and the way to be sure that w1 and w3 are same. So we come to this equation. With u2 is equal to 0, we get w1 twice w1 u1 square is equal to 2 upon 3. This equation gives, and when we use another non-zero equation, we get 2 w1 u1 to the power 4 is 2 by 5. If we divide this two equation, we get u1 square is equal to 3 by 5, giving u1 is equal to something wrong. Okay, u1 is equal to square root of 3 by 5. We consider P3 of u, Legendre polynomial of order 3. This is half u times 5u square minus 3. So the roots of it, the zeros or roots are u0, this is u2. u1 is equal to plus 3 by 5 and u3 is equal to minus root 3 by 5. That is why this is called Gauss-Legendre quadrature. So another point is that although we need to solve, now coming to the fact of the evaluation of w1 and w2. Knowing u1, if we put the value of u1 is equal to u3 in this equation, we get w1 which is equal to W3, and the value of W1, W3 in this equation gives you W2. So the weights are obtained. We see another thing, although we see that for n-point Gaussian quadrature we are to solve 2n simultaneous equation, but the u values, the specific values of the arguments are obtained from the nth order special function. As for example, if we integrate it between plus minus 1 limit, the zeros of Legendre polynomial of order n gives you the u values. There are integrations which so we need not to solve all these equations for determining u's. U's are obtained, and then the task is remain to evaluate w. The w can be a general expression for w can also be formed, but we are not going to this complicated algebra. So the Gaussian quadrature, in Gaussian quadrature we divide the interval into the zeros of special function, as for here the zeros of Legendre polynomial, and we evaluate the function at the functional value at this point and multiply the functional value with the corresponding weight and sum these products to get the integration. This technique is found to be very helpful and which gives the convergent result with very lesser number of points. There are functions which we want to integrate it from 0 to plus infinity. When we want to integrate function from 0 to infinity, it is found that Legendre polynomial is not a suitable one. Then one goes to Logar polynomial and seeks for the zeros of the Logar polynomial, and the corresponding technique is called Gauss-Logar polynomial. And for Logar polynomial, the weight factor w is of the order of e to the power x. And when we want to integrate the between limits plus minus infinity, from minus infinity to plus infinity, one switches over to Hermite polynomial and having the weight factor e to the power minus x square. Another type of integration is found using Bessel function, and in which case Bessel function of a particular order is used, and the u values are the zeros of the Bessel function and the weight factor is x. This is the basic technique of Gaussian quadrature formula, and in your program if you were asked to calculate a function, if you are asked to calculate this using n points formula, then n values of u and the corresponding w will be supplied. So you have to write a program which will read from file n values of u and the corresponding n values for w, and use use this formula u is equal to summation over I is equal to 1 to n wi phi of ui as the value of the integration. If you want to know the convergence, then we may increase the value of n. Say first n is 10, then increase n to 12, then to 14, and so on, and at each time we will check the value of u. If the desired level of accuracy is obtained, then the desired level of accuracy is obtained, then we stop our iteration, and if not, the iteration is continued until convergence is obtained. That's all about numerical or Gauss numerical integration. Next we shall take over the solution of ordinary differential, numerical solution of ordinary differential equation.